Imagine taking a notebook, a plastic bottle, a toaster, and a glass container and burning them in a fire. If the fire was hot enough, all the materials in these four things would break down into a gaseous mixture of molecules and atoms. If you make this fire hotter, all the atoms would break down into their component electrons and neutrons. If you go hotter still, these particles would break down into the fundamental particles of the Standard Model, things like quarks and leptons. And if you go even hotter, we're talking astronomical temperatures around 10 to the 31 degrees, or about 1,000,000 trillion degrees Celsius. All the quarks and leptons of the four fundamental forces of nature would break down into one entity, a kind of soup where all the fundamental particles and the underlying forces responsible for their behavior would meld into one. This is what is believed to have existed at the moment of creation, at the moment of the Big Bang. All the particles and forces of our reality came from this primordial soup. But this is the story of the four fundamental forces of the universe that, as far as is known, control everything in the universe, every movement, every phenomenon, and every process you can possibly think of. What is the nature of these forces? How do they work? And where do they come from? According to modern particle theory represented by the Standard Model of particle physics, all matter is composed of 6 quarks and 6 leptons and their 12 antiparticle pairs. But that's not all. Matter is subject to 4 fundamental forces that cause this matter to behave in certain ways and result in essentially every action that you see all around you and everywhere in the universe. These 4 forces are the strong force, which binds the nuclei of atoms by holding protons and neutrons together in their center, the weak force, which is responsible for some kinds of radioactivity, electromagnetism, responsible for electricity and light and is also the root cause of chemistry, and finally gravity, which binds us to the Earth and keeps the planets in their orbits around the Sun. Yet the most interesting aspect of this picture is that at a fundamental level, scientists believe that all the forces come from one underlying force or principle. And astonishingly, not only that, but according to current understanding, all 24 of the different fundamental particles and the 4 forces are one and the same at some deep level. This is the ultimate symmetry of the universe. Perhaps the best way to understand this and how these forces emerged is to visualize what happened at the very beginning of time, at the Big Bang, when everything was one. Time began not at 0, but at the smallest measurement of time that can be represented by our models of quantum mechanics, and that is Planck time. This is not 0, but pretty close from our perspective, 10 to the negative 43 seconds. This is not to say that nothing existed prior to this, but it is just the limit of our knowledge. We are ignorant of anything that might have occurred prior to this first epoch of existence. So this is aptly called the Planck epoch. All the forces and particles were one and the same, in a point smaller than the size of a proton. Gravity is thought to have separated from everything else shortly after this time period. So it was the first force to separate out from the other 3 forces. The temperatures at this stage of the universe were, as you might expect, astronomical, 10 to the 31 degrees Celsius, and the energies were on the range of 10 to the 19 billion electron volts or giga electron volts. If we ever develop a theory of everything, then it would explain everything that occurred up to this time. The strings of string theory and the loops of loop quantum gravity, if those theories are correct, come into existence and apply here. The next era, called the Grand Unified Epoch, lasts from the first Planck second, 10 to the negative 43 seconds, to about 10 to the negative 35 seconds. Up to this period, the remaining 3 forces, the strong force, the weak force, and electromagnetism, were all united. But shortly after this period, from about 10 to the negative 34 to 10 to the negative 32 seconds, the strong force separated from the other 2, electromagnetism and the weak force, which were united as one force called the electroweak force. Temperatures were now around 10 to the 26 degrees Celsius, and the energy was reduced to 10 to the 15 giga electron volts. If we ever discover the Grand Unified Theory or GUT, which unites the strong force with the electroweak force, we would need to model what happens at these energy levels and temperatures. Somehow this separation of the strong force is thought to have resulted or powered something called cosmic inflation. This is the momentary expansion of the universe, which went from something tinier than the size of a proton to the size of a grapefruit. This is a huge increase in size. It's analogous to something as small as a tennis ball becoming the size of the solar system in a very small instant. At 10 to the negative 12 seconds, called the quark epoch, the electroweak force split into the weak force and electromagnetism. These two now became separate forces. So at this point, all the four forces became distinct. The temperature of the universe cooled to 10 to the 15 degrees Celsius, and energies are about 100 giga-electron volts. We know a lot about the universe up to this era because such energy levels can be easily modeled in particle accelerators such as the Large Hadron Collider. So our understanding of the electroweak force is fairly robust. The Higgs field also exists at this stage as well. How do we know? Because about 100 giga-electron volts was needed to create the Higgs boson, and this can be done at the LHC. Now fast forward to today, 13.8 billion years later, where the average temperature of the universe is negative 270 degrees Celsius, and energy is on the order of 0.25 electron volts. Let's look closer at the four forces, and let's start with the two we are most familiar with, gravity and electromagnetism. They are similar in that their mathematical formulas look nearly identical. Newton's law of universal gravitation can be expressed as the following, where g is Newton's gravitational constant. Coulomb's law of electrical force between charged bodies can be expressed as the following, where k is Coulomb's constant. The first formula tells us that the gravitational force between any two bodies is proportional to the product of their masses and inversely proportional to the distance between them squared. Notice that the force extends infinitely far. This means that the Earth has a gravitational effect on not just the Moon and the other planets of our solar system, but also some effect on every other massive object in the universe. Mind you, this is a very small effect because the r in the equation would be very large for things very far away. So the force would be very weak, but it is non-zero. And since gravity affects anything with mass, this effect is the most influential force on a cosmic scale. But almost everything I just said also applies to electromagnetism. The electrostatic force between charges extends also infinitely far away. This means that a charged particle on Earth has a non-zero effect on a charged particle near Proxima Centauri, our nearest neighboring star, and charged particles everywhere else in the universe. And this force is much, much greater than the force of gravity. In fact, the magnitude of electromagnetism is 10 to the 36 times greater than the magnitude of gravity. So why isn't electromagnetism the most dominant force in the universe? The reason is because on large scales, electric charges of large objects tend to cancel each other out. Large objects tend to be neutral. So since a charged particle can only affect other charged particles, this force is mostly non-existent at large scales. If large things were not electrically neutral, this force would completely dominate our universe. But electromagnetism still has a big influence in our world. It is responsible for the nature of light, and it is the main force responsible for all the biochemistry taking place in our bodies and the rest of Earth. It's the basis of all chemistry. So now you have to ask, if electromagnetism is so strong, then what keeps multiple protons, each of which are positively charged, bound in the nucleus of atoms? According to Coulomb's law, if you do the calculations, the two protons of a helium atom experience a force equal to about 20 pounds. For something as small as atoms, this is a huge force. They should repel each other and fly apart instantly. The reason that protons don't fly apart is because they are kept glued together with a force that is even stronger than electromagnetism, 100 times stronger. And this force is creatively called the strong nuclear force. It is the strongest force in the universe. However, it extends only as far as the width of a proton. Remarkably, it is very small or non-existent beyond this length. This force has been described as Velcro. When two protons are really close, the force keeps them strongly bound together. But when they are further apart than the width of a proton, it's about non-existent. This force is not simply the opposite of electromagnetism, though, because it is also responsible for holding electrically neutral neutrons in the center of atoms as well. Even though this is a force we can't directly experience, the world has experienced its effect. How? Because you see, the release of this force is the energy behind nuclear bombs. The fission and fusion of atoms releases huge amounts of binding energy from the nucleus of atoms, which results from the strong force. The binding energy of this force is in fact responsible for most of the mass of any object, not the Higgs field as you might have thought. And when this binding energy is released, the mass of the atom is converted to energy in nuclear reactions. Then we get to the weak force. This is responsible for a type of radiation called beta radiation, which is the emission of electrons or its antimatter equivalent, positrons. One of the most important processes in nature is the beta decay of a neutron. This happens, for example, when a neutron decays into a proton, an electron, and an antineutrino. If this kind of decay had not occurred, then the universe would have been awash in a sea of neutrons and no atoms would have ever formed, and we would not have had life. This process is also important in making larger atoms stable because a similar decay called beta plus decay occurs when a proton is converted into a neutron, a positron, and an electron neutrino. It results in positron emissions, and this process allows for nuclear stability. Like the strong force, this force is also only effective at really small scales, but the range is even shorter than the strong force. Its effective length is only about 1,000th the diameter of a proton. Now I've tried to give you an overall perspective on the four fundamental forces. Classical mechanics has been and continues to be used to explain many phenomena that we can observe. Consider a planet orbiting a star. We can use Newton's laws to model it fairly accurately. If the planet were to somehow lose its kinetic energy or slow down, it would spiral into the star and collide. Now consider something conceptually similar, an electron orbiting the proton of a hydrogen atom. In this case, we could again try to use Newton's laws to model it. Instead of the attractive force of gravity for the star and planet, the two objects' electrical charges keep it bound together. This is where classical mechanics fails because, as we know from Maxwell's laws, an accelerating charge creates electromagnetic radiation, and the constantly changing direction of the electron creates an acceleration. This means the electron would constantly give up photons, losing energy in the process. It would thus spiral towards the nucleus and collide. But we know that no such thing actually happens in reality. Atoms are stable. An electron does not crash into the nucleus. Why? Because we were using the wrong tool to describe the model of an atom, classical mechanics. We have to use a new tool, quantum mechanics. Niels Bohr proposed that the electron maintains a stable orbit because its energy is quantized. It can only be in an orbit that is an integer multiple of a minimal quanta, and its lowest energy state is the lowest orbit that the electron can have. It cannot be lower. This minimal quanta, by the way, is proportional to the Planck's constant. In Newtonian physics, we think of objects as discrete particles having very specific and measurable properties, such as a mass x, momentum y, and position z. In quantum mechanics, our objects are wave functions described by some completely different mathematics. This is shown by the Schrödinger equation. which is perhaps the most important equation in quantum mechanics. Here, the location of a particle is unknown until the moment of measurement. We cannot know where it is beforehand. We can only know the probability of finding it at any specific location. Prior to measurement, the wave function depicts a kind of smearing out of its location. Thus, in the quantum mechanical model of the hydrogen atom, the electron is not spinning around the nucleus like a planet around a star. It's in some unknown location at some unknown distance from the nucleus. All we know is that the chance of finding the electron at any specific location or distance from the nucleus has a probability associated with it. And we can't determine the location in advance of measuring it. So the better model of the atom is like a cloud around a fuzzy nucleus. The white cloud represents the probability cloud of the location of the electron. Note that the nucleus too would be fuzzy as well, since it is also a quantum object, but its cloud would be more localized than the electrons. Now you might think this is a great model. We know everything now. We can stop here. But we can't, because quantum mechanics has some problems too. There are some things it cannot explain, and we get the wrong results, just like when we tried to explain the electron's orbit with the classical formulation. First of all, quantum mechanics is not relativistic. That is, it will give you wrong results if the quantum object is moving close to the speed of light. Schrödinger's equation simply doesn't obey Einstein's theory of special relativity. The practical result of this is that it doesn't incorporate a speed limit, the speed of light, needed to make causality work. For example, it allows for two measurements to influence each other faster than light. This would mean that there would be some reference frame in which the future could influence the past, breaking causality. A second problem with quantum mechanics is that it only tells you how a particle evolves over time. That is, how it goes about its business. It does not tell you how it is created or annihilated. So it can't account for things like beta decay due to the weak nuclear force, where a neutron transforms into a proton, an electron, and an antineutrino. In this case, quantum mechanics breaks down because it doesn't work if we change the number of particles. In the case of the beta decay I just described, the down quark of a neutron decays into an up quark, changing the neutron to a proton, and at the same time emits an electron and an antineutrino with a mediating W boson. This change to other particles can't be described by quantum mechanics. This is where quantum field theory explains things that quantum mechanics cannot explain on its own. So, what is quantum field theory? Well, it's a mathematical framework that combines classical field theory. A classical field would be like a magnetic field as described by James Clerk Maxwell, special relativity, and quantum mechanics. There is a field for every particle of the standard model. So in our beta decay example, there would be a field for the down quark, the W boson, the up quark, the electron, and the antineutrino. All these fields extend out in all of space-time. In other words, the fields are always there and exist everywhere, including inside your body. Now, although they exist everywhere and you can't see them, they are not nothing. They are teeming with virtual particles. These are particle-antiparticle pairs that get created and destroyed. So for example, the down quark field will always have some spontaneous creation of down quarks and anti-down quarks, which get created and annihilated almost instantly. They come in and out of existence constantly. These virtual particles can't be measured, but nature allows the creation of these virtual particles by letting them borrow energy from the vacuum, as long as that energy is put right back into the vacuum. This happens so quickly that it's as if nature doesn't register them as real measurable particles. We can visualize these fields as a kind of ocean. Just like the ocean wave has some turbulence, the fields always have a kind of turbulence, even in their ground state of minimal energy. This turbulence is due to the virtual particle creation and annihilation I just described. In these turbulent seas, if there's enough energy, a large wave can be created, which can be measured. These are the real particles. So in the up quark field, for example, an up quark will be created if there's energy of 2.3 mega electron volts, or MeV, which is the mass of one up quark. Two quarks will be created if there's energy of 4.6 MeV. So a particle is nothing more than an excitation in this field. These excitations are quantized, not continuous. So the fields can only create particles in integer increments. They cannot, for example, have 1.5 up quarks, only 2 quarks or 3 quarks, etc. Now energy can be transferred between two fields via a mediating boson field. This is considered an interaction or a force. Matter particles can't interact on their own without a mediating boson. So while in quantum mechanics there's no way for the neutron to split its energy into 3 different particles, a proton, electron, and an antineutrino, in quantum field theory this can be done via energy exchange between the fields. You start with the fields of all the different particles, which are always there, and you finish with the fields of the same particles. Some of them just have more or less energy after the exchanges of energies, depending on the interaction. So in our beta decay, for example, you start with the down quark field. This field transfers its energy to the up quark field and the W boson field. The W boson field then transfers its energy almost immediately to the electron field and the antineutrino field. So we started with 1 particle in the down quark field and we ended up with 3 particles simply by the fields exchanging energy. Note that although the number of particles changed, the total energy is always conserved. If you add up all the masses and kinetic energy at the beginning, they will add up to all the masses and kinetic energy at the end. In other words, the energy of the fields is the same before and after the energy exchange. So by having quantum fields, we can mathematically account for and model creation and annihilation of particles, as well as the mechanism of force exchange. The icing on the cake is that the theory is fully relativistic, meaning it's free of causality violations. But even this modification of quantum mechanics is not perfect. For example, it's still missing gravity. We do not have a quantum field theory for gravity. If we did, it would mean that we could model a field for the theoretical graviton particles, and gravity would be mediated between matter particles by the exchange of this graviton boson. So even QFT, which is extremely accurate for the forces and particles we do know about in the standard model, remains as yet incomplete. The fact that we don't have this tells us something. It reminds me of the saying that when you have a hammer as your tool, everything looks like a nail. Our tool is QFT. So far, everything we know has been a nail. So either gravity is not a nail, or maybe we just don't really know how to use the hammer. But still, in my view, QFT is probably the most beautiful theory in science, and here's why. Because it tells us that the universe and everything in it, including us and all living things, the whole planet, every star, every galaxy, and even things outside the visible universe are all connected. Everything, even our thoughts, dreams, and ideas are composed of excitations in the same quantum fields. And all these fields extend to not only all of space, but all of time. The universe is made of the same basic stuff, and we are all simply a series of excitations in it. So when someone says we're all one, or that we are all connected to the universe, this is not just a fanciful idea, but has a real physical meaning. I find this to be beautiful.
Consider an electric wire consisting of a long chain of protons and electrons through which flows an electric current, which corresponds to the motion of electrons inside the wire. Imagine now that we leave an object a certain distance away from the wire, which carries a positive electric charge. According to what we saw earlier, each proton in the wire repels the apple as their charges are both positive. At the same time, each electron attracts the apple with the same intensity. Overall, if we add up all these forces, they compensate each other, and the apple does not experience any net force. It remains motionless. Let us now throw the apple to the right. Strangely, we now observe that it is gradually repelled by the wire. While it is not subject to an electric force, the apple seems to be experiencing a mysterious force that pushes it away. This new force is very peculiar. It does not appear when the apple is motionless, but only when it is moving. Moreover, it seems to depend on the direction and the speed of the apple. This mysterious force, which appears when an electric charge moves around, is called the magnetic force. To understand its origin, we will have to review what special relativity teaches us. Before that though, let's study the situation not from an outside point of view, but rather as it is perceived by the apple in its own frame of reference. From this point of view, it is not the apple which moves to the right, it is the wire that moves to the left. Now, according to special relativity, the faster an object moves, the more its length gets contracted in the direction of motion. In this reference frame, the protons in the wire are now in motion. They will thus get contracted along the direction of the wire. The protons come closer to each other. Conversely, the electrons appear to be moving more slowly because the entire wire is now moving to the left. They therefore get slightly stretched compared to the previous point of view and move away from each other. Overall, when we add up the forces acting on the apple from this point of view, they no longer cancel out. There are more positive charges, protons, than negative charges. Therefore, the wire exerts a repulsive force which pushes back the apple. By considering special relativity, we see that the electric field of a charge gets distorted when it starts moving. This phenomenon involves the appearance of a new force, the magnetic force, which is in fact an electric force perceived from a different reference frame. Similarly to the electric field, we can summarize all these behaviors under another field, the magnetic field. When an electric charge moves, it creates a magnetic field around it, which can be represented as arrows revolving around the direction of motion. The magnetic force is a consequence of special relativity, and the behavior of the magnetic field is therefore rather strange. In a magnetic field, a stationary particle does not feel any force. On the other hand, a moving particle experiences a force whose strength depends on how perpendicularly the particle moves in relation to the magnetic field. This force tends to pull particles in circular trajectories, the size of which depends on their mass, their speed, the intensity of the field, and the electric charge.
The hypothetical mechanism is the following. The material ejected from the explosion is a plasma, which results from gases heated to such extremes that they lose electrons from their atoms. In addition, the rapid rotation of the dying star twists up its magnetic field. This means that the easiest path of escape for any of the charged particles being ejected from the hypernova is along a narrow beam at the poles of the rotation, since the magnetic field can't get as tangled in that direction. The particles being ejected are largely electrons. The twisted magnetic field causes the electrons to travel in a kind of helix, like a DNA molecule. If the electrons are moving fast enough, the rapid change of direction can produce high-energy photons, or gamma rays. Gamma rays can also form if extremely fast electrons crash into photons. The transfer of energy to the photon can cause it to gain energy and become a gamma ray.
Computer simulations allow us to reconstruct the formation of our solar system 4.6 billion years ago. We use the laws of physics to create these virtual experiments in order to figure out how planets took shape. After the Sun ignited, most of the material around it had flattened into a disk of gas and dust. We can zoom into a simulation of a portion of the thin disk, a small piece of the universe in a box. Here, a dense swarm of objects clump together to form what astronomers call planetesimals. This simulation addresses how planetesimals form from much, much smaller particles, the size of pebbles. Pulled together by gravity, some planetesimals formed the planets, while others became asteroids and comets and dwarf planets. As the planets accreted, they carved out gaps in the disk. But the solar system remained quite cluttered. If we look at the orbits of the planets and accelerate the passage of time, so 1 million years pass by every 10 seconds, we can watch how the debris cleared. In this simulation, the giant planets, Jupiter, Saturn, Uranus, and Neptune, shift their orbits, and many unlucky asteroids and comets and dwarf planets get kicked out of the solar system. The migrating giants wreak gravitational havoc. The distribution starts out quite flat, but as most small objects get tossed out, others settle into stable orbits that allow them to coexist safely with the planets. But their orbits aren't as flat as the original solar system. Instead, they follow trajectories far above and below the plane of the planet's orbits. Today, the orbits of Pluto and other Kuiper Belt objects show exactly this pattern. The tiny icy worlds that inhabit the outer reaches of the solar system provide evidence for an ancient interplanetary transformation.
Let's start with a quick review of what the interior of the Earth looks like. Beneath the thin crust and 2,900 kilometers of solid mantle lies Earth's core. The 2,400 kilometer thick outer core is molten iron and nickel and some other stuff. I'm not talking about lava here, I'm talking about liquid metal with the viscosity of water. Beneath this layer is the inner core, a 1,200 kilometer radius ball of solid iron. It's solid because of the pressure at that depth. At around 5500 Kelvin temperature, it would instantly melt at lower pressures. Everything is moving down there. The solid core rotates slightly more quickly than the surface. The core's day is a few seconds shorter than a surface day. The outer core has a rotation gradient. The outer layer actually rotates a bit slower than the surface, but it speeds up as you get deeper. And that motion gets even messier. The interior of the Earth is cooling down very slowly, which means the liquid outer core is freezing onto the solid inner core. As the inner core grows, it releases non-iron impurities that flow upwards, joining convection streams. These flows are then twisted into helices by the Coriolis force, the same effect that produces hurricanes on Earth's surface. It's all of this motion that together produces Earth's magnetic field.